All right, this is the last of the graphs. Thank goodness. This is 1.3 velocity versus time graphs and 1.4 acceleration versus time graphs. And although it seems like there's a lot going on here, this is actually short and sweet. You'll be pleasantly surprised, I think. Starting with velocity versus time graphs. The slope of a velocity time graph represents acceleration. So when we do slope, rise over run, we get rise as being our v's and our run is our t's. So again, if we look at rise over run from the point of view of the graph, our rise is velocity, our run is time, so change in velocity over change in time. And again, you'll recognize this as our formula for acceleration. So we have constant or uniform acceleration, and this is represented by a straight angled line on a v versus t graph. And we also have zero acceleration or constant velocity, which is a horizontal straight line. So we've seen these shapes before in a position time graph, but they mean different things in a velocity time graph. So again, just to recall, if I had a position versus time graph, if I had something like this, this means stopped on a position time graph. But when it comes down to this section on a velocity time graph, this means no acceleration, which means I have my cruise control on. So I'm going at a constant velocity. So depending on the graph, these shapes mean different things. Again, on a position time graph, when I saw that straight diagonal line, that meant that I had a constant velocity, whereas the straight horizontal line now means a constant acceleration. And that can be in either direction. The other thing I can do with a velocity time graph is I can actually solve for displacement. So how far has the object traveled? And this is the area under the graph. So for instance, and we'll do this in a minute, this graph has sort of a weird shape. So what we want to do is we want to break it up into triangles. Oh, that's awesome. And rectangles. Just a reminder, that's the doorbell that's going off here, and hopefully they'll switch it so we don't all have to hear it in the entire school. So triangles and rectangles. So for the area of a triangle, we would do a half base times height. Rectangles are base times height, and then we would add all of the areas together to get the entire displacement. So let's try it out. Calculate the slope for the first 4 seconds of travel. So the first 4 seconds takes us to here, and we want to calculate the slope. This is a velocity over time graph, so our slope is acceleration, v2 minus v1 divided by t2 minus t1. So again, you're going to choose any 2 points. I'm going to choose this point and this point, keep it easy for myself. v2 is 8 meters per second. I'm going to add direction here. Let's do east because it's a vector. It has to have a direction as we know it. Looks like it got cut off. And my v1 is just a 0. And my t's are 4 seconds and 0 seconds. So my final answer then, of course, is going to be 2 meters per second squared east. I know that unit can be tricky with acceleration. And that is my final answer on that one. So let's try the second calculation, and that is our displacement. And this time they want the displacement for our entire trip. So it's the area under the entire graph. So let's break it up into triangles and rectangles. So I'm going to cut this one here. So this will be one triangle. I'm going to cut it here. That'll be a rectangle for my second area, and then my third one will be another triangle. You can cut it up as much as you like, but try to keep it simple. That's the sort of the name of the game. So for my area, remember I'm calculating displacement, so the first one will be a half base times height. So my base is 4 seconds. My height is 8 meters per second. Again, we're going to keep that as east. Okay, and then we'll work out the math. So the area for the first one is going to be 16 meters east. And let's do the second one. So D, we can call this D1, let's call this D2. Second one is our base times height, so we're between 7 and 4 in the time, so our base is 3 seconds. And our height is 8 meters per second east. So again, we get a value of 24 meters east. Again, when we look at the units here, seconds times meters over seconds, seconds is canceling, which makes sense because this is a displacement. And finally, our D3, we have 7 to 10 seconds as our base, so another 3 seconds covered here. And again, our height is 8 meters per second east. And because this is a triangle, this is going to be halved. So it's the same math as above, divided by 2, so we'll have 12 meters east. And then we're going to do our overall displacement. We could even call it resultant displacement here. So the entire travel is going to be all 3 values added together. So we get a total of 52 meters east. And that's our final answer. The last type of graph we sometimes see is an acceleration versus time graph. A straight horizontal line represents constant acceleration. And the area under the graph could be used to calculate velocity. We don't do a ton of work in this area. We will see this graph once, an acceleration versus time graph, but we don't use it all that often. So here's an example. Again, let's say the acceleration here was 5 meters per second squared west. You can see when it's horizontal like this, that acceleration, no matter what time we look at it, is always the same. So this is something that's constantly accelerating at a steady pace. So that's the shape of the graph that we're going to end up seeing. So we're not going to get too complicated in this area. Homework time! I'm so excited. So these are the questions I want you to try in this area. Have fun. It's going to be great. And guess what? This is the last of the graphs. We're going to practice a little bit more, and then we'll do a quiz next week, and then we'll say goodbye to graphs. Yippee!